Welcome everyone to this video. We're going to talk about some more reaction mechanisms, specifically enzyme reactions. Okay? So, typical enzyme reaction has the following mechanism. You have some enzyme E, some substrate S that react together to form some enzyme substrate compound. That's typically a very fast setup. You can establish some type of equilibrium between those two guys potentially. Okay, and then you often have a slower step where that enzyme substrate compound forms some product and spits back out the enzyme. Okay, right. The rate for this mechanism is given kind of by that slow step. The rate is equal to Kb times concentration of enzyme substrate, right? But we obviously don't want the concentration of enzyme substrate in our overall rate law, right? Because we can't measure that. We don't really know what it is as the reaction is going on, okay? And it's intermediate, so we want to use something like the steady state approximation to get rid of that. Right, so the steady state approximation for this mechanism, for the enzyme substrate compound, right, is Ka times concentration of E times S minus K minus A times concentration of ES minus Kb times concentration of ES, right? Because it's a product in the forward reaction, it's a reactant in the reverse, and a reactant in the second reaction here, okay? Using that, we can solve for the concentration of the enzyme substrate in terms of concentration of the enzyme and the concentration of the substrate, okay? Note here that that concentration of enzyme is the free enzyme, right? Some of our enzyme, as this reaction is going on, is occupied in the enzyme substrate compound, right? And so we need to somehow, right, kind of get rid of that dependence, right? Because we don't really know, again, how much enzyme is tied up in enzyme substrate, right? But we know, say, what is our initial concentration of the enzyme. And so we're gonna do some extra manipulations here in order to get our final rate law in terms of the initial concentration of the enzyme and our concentration of the substrate instead of concentration of the current free enzyme and the substrate. So to do that, we know, right, that the concentration of the free enzyme plus the concentration of the enzyme bound to the substrate is got to equal the initial concentration of that enzyme, okay? Because, again, that enzyme is not being consumed, right? And so you can use what the concentration of the enzyme substrate is in terms of the concentration of the free enzyme and rearrange that a little bit, okay? To get the concentration of the free enzyme equals Km times the concentration of the enzyme substrate divided by S, where Km is defined as follows. Okay, we plug that in for E, right? So we plug in this into this expression up here, right? Pull out the enzyme substrate, and then we have enzyme substrate times 1 plus Km divided by S is equal to the concentration of the initial enzyme. Okay, and so rearranging that, right, we can just write the concentration of the enzyme substrate in terms of the free enzyme, and then this Km, right, and then what we're going to do is we say that the substrate, there's lots of it, so its concentration is basically the initial concentration, and so we have something like this, okay, and so then our rate law just becomes this expression here, okay. So finally, then the mechanism here, right, for the Nicholson-Menten type mechanism for enzyme kinetic reactions, right, gives us this final rate law. Okay. Now often I wrote this later on in terms of the initial concentration of S naught, right, and that's often what's used. But technically, right, you don't need to use that initial concentration of the substrate, right? You could just write the rate law as Kb S E naught, the initial concentration of the enzyme, S plus Km, right? Where Km is Kb plus K minus A over Ka, right? This ratio of rates, right? Where Kb and K minus A are the rates in which you lose the enzyme substrate compound, and Ka is the rate in which you form the enzyme substrate compound. So Km gives you kind of an idea of the binding of that substrate to the enzyme, right? Because right, the faster you form the enzyme substrate compound compared to the speed in which it's being broken, right, is giving you an idea that this substrate binds the enzyme very quickly, but then is stuck there for a while, right? So very small values of Km indicate very strong binding from the enzyme to the substrate, or at least very slow process of forming the product, right? But if Km is a very large value, then that means after the substrate binds to the enzyme, it either quickly detaches because it's just not very strongly bound to the enzyme, or quickly forms product depending on the size of Kb versus K minus A, right? But you can get the idea of the rate in which forming the product, right, from Kb here, okay? And so in the case of low concentrations of the substrate, this rate law simplifies down to this expression, which is first order in both the concentration of the substrate and the initial concentration of the enzyme. But for very large concentrations of the substrate, it simplifies down to where the rate is just dependent upon the concentration of the initial enzyme and how fast that enzyme can form product, right? And the reason is right, for very high concentrations of substrate, you should have enough substrate that you formed an equilibrium between the substrate and the enzyme bound with the substrate, right? And you've kind of saturated those enzymes with substrates, right? So the rate in which you're forming products really just depends on how much enzyme you have in solution, right? And then kind of the rate constant, right? How fast that second reaction is, okay? And again, this is known as the Michelson-Menten mechanism, okay? And it's used all the time in studying enzyme kinetics in biochemistry. So the long breaks between some of these slides is, I'm having issues for some reason clicking between slides. But so now we're going to talk about what if we have the same type of kinetic reactions, but we throw in an inhibitor in these reactions. So an inhibitor is something that stops that kinetic catalytic reaction that the enzyme's doing. Okay, this is how drugs work all the time, right? They try to inhibit some sort of enzyme reaction within the body, right? And so there's two types of inhibitors that one can talk about, and we'll kind of talk about both of them. Okay, this first type of inhibitor that we're going to talk about here is called a competitive inhibitor. So a competitive inhibitor competes with the substrate in terms of binding with that free enzyme to form either enzyme substrate or enzyme inhibitor compound. Now the enzyme inhibitor compound, right, doesn't undergo any type of further reaction, right? The idea is that the inhibitor binds with the enzyme and occupies the enzyme, so it cannot bind with the substrate, okay? And it's only the enzyme substrate compound that undergoes any subsequent reaction to form the product, right? And so, right, again, the rate of this reaction is going to be related with this typically very slow step here, right? VK2 times concentration of S, right? Now K2 was KB, you know, before when we talked about just enzymes, so just kind of keep that in mind, right? This is sort of KB, Ka, K minus A, right? In terms of things like that, right? Again, right, we don't want things in terms of the enzyme substrate compound, right? So we can use the steady state approximation. Okay, now the steady state approximation, okay, we have kind of the same thing as we did before, right? Because this reaction here, right, doesn't affect the concentration of the enzyme substrate directly. It only indirectly affects it by changing the concentration of the enzyme, okay? So we're going to follow the same kind of procedure, right? Where again, we have the same steady state approximation as a normal enzyme reaction, okay? And again, you can write in the rate of that reaction in terms of enzyme, the free enzyme concentration, the substrate concentration, but again, we don't want the free enzyme concentration, and so we got to substitute that out. To do that, right, again, we're going to find the same Km expression, right, as before, okay, but now the free enzyme concentration is equal to the initial enzyme concentration is related to the free enzyme concentration plus the enzyme substrate plus the enzyme inhibitor. Okay, right? And that enzyme inhibitor is again some sort of kind of intermediate, so we use a steady state approximation for that to find, that the concentration of the enzyme inhibitor is just equal to K3 over K minus 3 times concentration of enzyme times concentration of the inhibitor. This K3, K minus 3 over K3 is Ki. This is the inhibitor equilibrium constant, right? This is an equilibrium constant. Oops. Right, that's an equilibrium constant, okay? Right, and so the enzyme inhibitor concentration is just related with the free enzyme concentration times the free inhibitor concentration. Okay, so if we combine those relationships between the enzyme substrate, and enzyme inhibitor, okay, we get that the enzyme inhibitor concentration is related with the inhibitor concentration, the enzyme substrate concentration, and the substrate concentration. And then finally, we can plug that into this expression here, do the same substitution, right, for the free enzyme concentration in terms of the enzyme substrate, okay, of Km times enzyme substrate divided by the substrate concentration. We get this expression here, okay. That expression, right, from the last slide, we just pull out the enzyme substrate concentration, divide all this wonderful stuff onto the other side, okay, right, to get that the enzyme substrate concentration equals this expression here, okay. Ki, the equilibrium constant for the inhibitor, times the concentration of the substrate, times the initial concentration of the enzyme, divided by Ki times the substrate concentration, plus Ki times M, plus Km times concentration of I, right? And so we plug that in, right, and we get this final rate law expression, right, which is similar, right, our rate law expression without the inhibitor was, say, K2 using that same notation, K2 S E naught over, what was it, S plus Km, right? Which, right, you relate these things if you divide the Ki on the top and bottom, right? Right, and so we'll put Ki here, right? Then we get a very similar expression, right? K2 times S times E naught divided by S plus Km. There's just this extra term plus Km times the concentration of I divided by Ki, right? And so, right, if we kind of relate that back, right, we have a very similar expression. And so how does this inhibitor affect the rate of the reaction and things like that for the substrate with the enzyme, okay? And so if I want to look at what the maximum rate is with respect to the substrate, right, that maximum rate is just going to equal, K2 times E naught, right? And plugging that in, we get this expression here, okay? Which again, comparing, so by definition, the maximum rate is K2 times E naught, right? It's right, assuming that, right, this maximum rate is basically assuming that, like, the binding with the substrate, or the substrate binding with the enzyme is extremely fast, right? That this is the limiting step, and it just depends on the concentration of the initial enzyme. That's all that's affecting the maximum rate, right? And so plugging in what that maximum speed is, the maximum rate is, to the expressions, right? Again, we can compare without inhibitor to with inhibitor, right? And again, the only difference is this extra term that appears on the bottom, okay? And so, right, how that inhibitor affects things is you can almost write the inhibitor expression as sort of this, the same thing here with the Km prime, where Km prime is the original Km Michelson-Menten constant, which again is related with the binding of the substrate to the enzyme, how strong does it bind to the enzyme, right, plus this ratio here, which is the concentration of the inhibitor divided by its equilibrium constant, which its equilibrium constant is related with the strength that it binds to the enzyme, right? Ki, right, is related with kind of ratio, right, of the enzyme inhibitor with the enzyme, right, and the inhibitor, right? And so it's related with this ratio, right? And so the more this ratio favors the products, right, the larger Ki is, right? The stronger this thing binds with the inhibitor, right? And things of that nature, okay? So again, there's a lot we can learn from the values of Ki and Km about these enzymes and inhibitors and substrates and things like that, right? And basically with the inhibitor, right, you end up having the same maximum rate, right? So eventually this guy gets to the same maximum rate, right? These two plots. But it does so more slowly, right? So the maximum rate is the same, okay? Right, that initial rate is the same as 0, right? It's just that without the inhibitor, it grows much more rapidly than with the inhibitor, right? It's much slower growth, okay? If you follow the same procedure for an uncompetitive inhibitor, okay? An uncompetitive inhibitor basically binds with the enzyme substrate compound to form this enzyme substrate inhibitor compound, okay? And we define the inhibitor constant K prime here, again, this equilibrium constant related to the ratio of the rate constants for this equilibrium reaction, okay? You get a similar expression, okay, right, where now it's just that the substrate in the denominator, right, is multiplied by this extra term here, okay, and how this affects the rate of your reaction is it affects actually what the maximum speed is, and the maximum speed now is reduced based off of how strong this inhibitor is, as well as the concentration of the inhibitor, okay. And then we'll note here, we talked about a competitive inhibitor, an uncompetitive inhibitor, and then a non-competitive inhibitor basically does both things. It binds the enzyme when the substrate is bound and when it's not bound. Okay. And so these inhibitors often are plotted using this Lineweaver-Burke plot, okay, where you plot the concentration of 1 over the substrate versus 1 over the rate, okay? What you then get is some different things, right? So for competitive inhibitors, you get the same y-intercept, but different slopes, right? So that's, again, saying that the maximum rate's the same, but it just takes a different amount of time to reach it. For an uncompetitive inhibitor, the slopes are the same, right? So how much the reaction speeds up with the substrate doesn't change, but the maximum rate does change, right? And then a non-competitive inhibitor has both effects, right? That the slope changes as well as the y-intercept changes in these plots, right? So you can, if you have some inhibitor and you want to know is it competitive, uncompetitive, or non-competitive, right? You can do this type of plot where you measure the maximum rate of your reaction, right? Versus 1 over that rate versus 1 over the substrate concentration. You'll get straight lines, and then how those straight lines vary with and without the inhibitors will tell you a lot about what type of inhibitor you have and how it works with your enzyme, right? Which is very key stuff that's studied all the time in biochemistry and in pharmaceuticals and other things of that nature, okay?